Greetings, nuclear energy lovers. My name is Zechariah Kitzhaber. I received my PhD in analytical chemistry from University of South Carolina in 2024, and I'm continuing to develop expertise in spectroscopy and instrumentation as a postdoc at Oak Ridge National Lab. My research is focused on applying spectroscopy methods and developing sampling techniques to solve challenges in nuclear energy. To put it briefly, I'm using lasers to monitor next-gen nuclear reactors with aerosol sampling. Let me begin by explaining laser-induced breakdown spectroscopy, or LIBS. This is a technique for determining the elemental makeup of a sample. A high-energy laser pulse is used to rapidly heat and vaporize the sample. Molecular bonds are broken, electrons are stripped from nuclei, forming a microplasma. As the plasma cools, high-energy atoms relax, giving off characteristic atomic emissions. By measuring the wavelength and intensity of these emissions, the composition of the sample can be determined. This works for solid, liquid, gas, and aerosol samples with little to no sample preparation. This makes LIBS a choice technique for monitoring molten salt reactors, a type of advanced nuclear reactor that uses a high-temperature molten salt as the primary heat transfer fluid, and in some cases as liquid fuel. These molten salt reactors, or MSRs, are more efficient and have enhanced passive safety features. But the composition of the molten salt and reactor off-gas need to be constantly monitored to track fission products and detect possible contaminants, for example from moisture, oxidation, or corrosion, to ensure safe and efficient operation. My research is focused on developing LIBS as a technique for online real-time monitoring of MSRs using aerosol sampling. This is done by sparging, or bubbling gas through the molten salt to produce aerosols and transport them through a gas stream. This gas stream can then be analyzed by LIBS for simultaneous real-time monitoring of major salt components and detection of fission products and impurities as gases or solids. LIBS can quickly detect small changes in concentration, with detection limits at the part per million level, and high-resolution instruments can measure isotope ratios. The choice of gas and flow rate are very important, and an advantage of sparging is that it performs best at low flow rates, requiring less material and producing less waste. Techniques like this will help bring about the next generation of nuclear energy. As I move forward in my career, I hope to continue to develop new ways to apply spectroscopy to improve and advance nuclear energy technologies to build a better and brighter future for all of us. Thanks to the amazing team at ORNL who helped make all this happen, with funding from the DOE Office of Nuclear Energy Molten Salt Reactor Program.